This is Math Light, and here's our lesson on scientific notation. All right, when do you use scientific notation? What's its purpose? All right, well, its purpose is to enable you to write very large or very small numbers using powers of 10. Very large or very small numbers using powers of 10. Now, we'll practice with some numbers that aren't quite so large or quite so small because we want to teach you the concepts. But it's really for very large numbers or very, very small numbers. And so we use scientific notation, and it involves powers of 10. And so the reason it's in the sheet is we just learned some exponent rules, and we're going to figure out how they apply to this scientific notation and these powers of 10. All right, I've got an example for you here. I've got my wedding band off to the right, and that is my wedding band there. And I was curious, how many atoms of gold are in my wedding band? All right, so to do that, first I had to go down to the lab. I had to weigh or figure out the mass of my wedding band. And it was 2.3 grams, okay? So then I had to look up on the periodic table how many grams of gold in 1 mole of gold. And the periodic table told me this, that every 1 mole of gold is 197 grams. Now you might say a mole, I thought that was an animal. Yeah, I got them in my lawn, they're driving me crazy. But no, a mole is a unit of measure, like a dozen is 12, like a gross is 144. A mole is a big, big, big number. And here's the number, 6.023 times 10 to the 23rd is a mole. Now that's ginormous. That is really, really, really large. It's a gigantic number, something like 600 billion trillion. Really big number. All right, well now my moles can divide out, and I'm in atoms, the units that I want. So if I multiply my 2.3 times 6.023 times 10 to the 23rd, divide by my 97, and I'm going to figure out how many atoms of gold I have, and it's 7.032 times 10 to the 21st. Now, you got to get a sense of just how large this number is. So let me see if I can write it for you. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21. All right, there we go. It's that many millions. Okay, it's that many billions. Okay, it's that many trillions. Okay. It is a ginormous number. All right, you see the value of scientific notation, and I hope indeed you do. And so what is it for? For very large numbers, for very small numbers. Okay, let me give you a progression here, try to help you understand powers of 10, because it's very important that you understand powers of 10 if you're going to be able to deal with scientific notation. All right, I hate when my screen does that. Let me go back here for you. Okay, so let's go ahead and take a look here at some powers of 10. So we know that 10 is 10 to the first, right? So if I had this scientific notation number, 3 times whatever, 10 to the whatever. If I had 3 times 10 to the first, that number is 3 times 10, or 30, right? Does it make sense? The number is just 30. 100 is 10 squared, right? So if I had 3 times 10 squared, it's 3 times 100, or the number would be 300. And you can keep going here. 1,000 is 10 cubed, so 3 times 10 cubed would be scientific notation. It's really 3 times 1,000, or 3,000. Okay, I don't need to keep going with the example. I think you get the idea. But it is important that you know your powers of 10. So the 10,000 place is 10 to the 4th, 100,000, 10 to the 5th. You should know that 10 to the 6th is a million. What's a billion? 10 to the, and hopefully you're thinking 9th, and trillion, 10 to the 12th. Okay, so look, this is all we're doing. We're just changing the form. The value is exactly the same, just changing the form. Okay, on the other side, remember how we dealt with negative exponents? Well, 0.1 is exactly the same as 1/10. And 1/10 is the same as 10 to the negative 1. So when you have 3 times 10 to the negative 1, you're saying 3 times 1/10, or 3 times 0.1, and the value is 0.3. And you just keep going now with the negatives. .01 would be 10 to the negative 2, and 001, 10 to the negative 3. Now, by the way, let me pause here for a second. Let's go back on the left-hand side. Notice something with the zeros and notice something with the exponent. Notice how many zeros and notice the exponent. You see the correlation? All right, you probably figured that out already as I was going through. I hope you did. So the power of 10 on the big side matches the zeros, or the places, really. On the right-hand side, notice that 0.1, so the negative 1, there are no zeros. Negative 2, there's 1 0. Negative 3, there are 2 zeros, and we keep going on. So negative 4 is going to have 3 zeros at the decimal place. Negative 5 is going to have 4. Negative 6 is going to have 5. 1 billionth, negative 9, and 1 trillionth, negative 10. Okay? Scientific notation, scientific notation, scientific notation. Okay, so how do we do it? That's pretty simplistic. Let me get rid of my box here. Let me extend my screen a little, if it'll cooperate with me. Too far? All right. So what's the procedure? How do you convert from standard notation or normal notation to scientific notation, right? Standard or normal notation to scientific notation. Okay, well, you write all the non-zero digits and all digits in between them. I'll show you what I mean by that in a minute. All right, this is important. Make sure you always place the decimal point after the first digit. After the first digit. So any number in proper scientific notation, the first digit will be always a 1 through 9. Could be positive or negative, doesn't matter, it's going to be 1 through 9. Okay, then you write your times 10. Then you got to figure out the exponent, okay? So you got to figure it out. The exponent will be the number of places the decimal point moves, and I'll show you that in a minute. And if you got to move the decimal point left, then it's a positive exponent. And if you have to move the decimal point to the right, it's a negative exponent. Okay, so let's put this into practice, okay? So digits after times 10 places, positive and negative. Okay, here we go. So all of that's right there again for you, so we can take a look. So here we've got B here, convert the following to scientific notation. So look at number 1. Okay, so for number 1, I have to write all non-zero digits and any zeros in between, well, are none. Okay, it's just a 4 out there. Next, I place the decimal point after. Now, usually for just a single digit number, we won't put the decimal point after it. Okay, so that, if it's just a single number, you usually don't write the number 5 decimal point, right? Just write 5. Okay, but we know that. All right, times 10. And now we have to figure out how many places the decimal point moved. So look, it was here, right? It wasn't shown, but we know it's there. So how many places did it move? 1, 2, 3, 4, 5, 6, 7, 8. 8 places is where it moves to get it just after the 4. So this number is 4 times 10 to the 8th. See the idea? 4 times 10 to the 8th. And if I were color coding, I would have used green there because I was moving left. All right, I'll do that next time. 4 times 10 to the 8th. Okay, let's do another one here. Negative 70, what is that? $1,800,000,000. Okay, don't let the negative scare you. So what are you going to do first? You're going to write all non-zero digits and any zeros in between. See, I need that 0 between that -7 and that 8. Second step, I'm going to place the decimal point after the first digit. Remember, proper scientific notation, the numbers are always between 1 and 9, that first digit. Okay, next times 10, and now you got to figure out your decimal point. Okay, pause it if you want to and figure it out. If not, here we go. All right, it's right there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is negative 7.08 times 10 to the 10th. Let's do another one. All right, so here's one now. Notice how this is a small number, right? Notice the decimal points to the left, all the digits to the right. Okay, so we're going to write the digits, just a 5 on this one. Again, don't need the decimal point after it, times 10. And now let's figure out the exponent. 1, 2, 3, 4, 5, 6, 7 to get it after that 5. Now be careful, it's a small number. And we move into the right, so this is -7. 5 times 10 to the -7. Be careful there, it's got to be negative. gotta be negative. All right, why don't you try, pause the video and try this one. Now, before you do that, let me say this. There's a reason why that last digit is bold and in blue. You have to include it. Zeros that end a number to the right of the decimal point are significant, meaning they're there to show you the accuracy of the number, and therefore you should include them in your scientific notation. So here, let's do the first part. So it's going to be negative 6.80. Okay, I had to keep the negative because it's a negative number. Then the 68, and I need that O because it ends the number to the right of the decimal point, times 10. And let's now figure out, go ahead and pause if you want to figure out the exponent yourself. 1, 2, 3, 4, right? Move 4 places, and remember we're negative here. Negative 6.80 times 10 to the fourth. Negative 6.80 times 10 to the fourth. Okay, so what's next? All right, we just moved everything. That's great. See if we can go back here. All right, we'll get there. My board likes to do things that only it knows what it's doing. Okay, let's go ahead and continue on here. See, let's go back the other way now. Let's go to standard notation. Okay, so now you have to go backwards. First off, note your exponent. Okay, it's a positive exponent. It's going to be a big number. And all I really have to do is I just have to take my exponent 5 places to the right. 1, 2, 3. I need a placeholder. 4. I need another placeholder, and that'll put it there. Okay? So if you notice, I can go 1, 2, 3, 4, 5. So I'm going to rewrite this. Proper notation. And it's 810,200. The decimal point has to move 5 places to the right, and you'll need 0 placeholders if necessary. So 4.6 times 10 to the 8th. Now on this one, you're going to need a lot of 0 placeholders, right? So you need the 4 and the 6, and this is, 1. And so how many more zeros do I need? 7. 1, 2, 3, 4, 5, 6, 7. Okay, because I had to move 1 for the 6, and then there's 8 places I had to move. So let's watch. So that was 1, 2, 3, 4, 5, 6, 7, 8. Sure enough, right? Okay, so let's see. Let's make sure we figure out where our commas go. Rewrite it. 460 million is this number. Now again, if you learn your powers of 10, you should look at that and say, "Ooh, that's 460 million." If you know your powers of 10. You look at this and you say, oh, that's the 100,000 power, 810,200. See, if you know your powers. All right, it's a whole lot easier that way if you know your powers of 10, hence the beginning of this lesson. Okay, be careful on the negative side. Now see, again, if you know how your zeros go, I know that this is going to be, and I like to put a 0 in front of my decimal point, right? And I know there's going to be 3 zeros and then my 8. Now you might say, Mr. Scarfy, how did you know that? So let me show you, because this is the way you would do it, right? Your decimal point would be here, and you have to go 4 places. 1, 2, 3, 4. See, I ended up at the 4th. So you would start with the 8, and you would add zeros to the left. So this is how you would do it, right? You're right here, and you would go, all right, 1, 2, 3, 4. Unless you figure out your powers of 10, and then you don't have to do all that. All right, again, let's clean this up. 0.0008. Do you need the 0 in front? Not necessarily. It's up to your teacher. Do whatever your teacher prefers you to do in that situation. Okay? Negative, same thing. Don't worry about it. The negative is just going to be out in front. Times 10 to the negative 3. Again, if you want to, I'd pause this video. See if you can do that one yourself. Okay, so we're negative 0. And I know I'm going to have 2 zeros before my 260. And again, notice it moved 1, 2, 3 places to the left. All right, but again, if you learn the powers of 10, it'll make life a little bit easier for you. All right, couple last concepts here. Make sure that you always put your answer into proper scientific notation, okay? Make sure you always put your solution in proper scientific notation. Proper scientific notation remember that first digit has to be between 1 and 10. So watch how this works. Because I have to make this number smaller, because I needed it to be 3.82. If this part gets smaller, then the power of 10 has to get larger by the same amount of places. That went one smaller, that goes one larger. See how that works? One smaller, one larger. All right, couple examples. See, this one's off. I'm gonna do this one in blue, so watch. 1, 2, 3, larger. What has to happen to this? 3, smaller. Right? They always work opposite each other. So for this to be 8 times 10 to the what? You have a positive 1. So really, the question is a 1 minus 3. So 1 positive, 3 negatives leaves you 2 negatives, right? 8 times 10 to the negative 2. Okay, let me show you these last two. I would pause the video and go ahead and do them, and then turn it on and see if you got them correct. Go ahead and do C and D. Pause the video, try them, and then turn it back on. Okay, so here was your logic. 4.321. I got 2 smaller, so I need to be 2 larger. Remember, with negative exponents, the less negative, the bigger. So 2 larger from a negative 5 is to a negative 3. In this one, 8.4 moved 1, 2, 3, 4. So I got 4 larger. I need to get 4 smaller. Again, we got to get more negative. 8.4 times 10 to the negative 13. Hey, scientific notation for very large numbers or very small. Don't neglect to understand and learn the powers of 10. It'll help you well if you know your powers of 10.